Okay, this is a solution to number 5 on Intro to Beam Stresses. You have a wall on the left and a beam with a fixed joint coming out of the wall and a triangular distributed load like this. The maximum value of the distributed load is 10,000 newtons per meter. The length of the beam is 1.5 meters. And we're neglecting the weight. Okay, calculate the internal loads and then calculate the XX normal stress. First, we have to come up with the reactions at the fixed joint. So if I do a free body diagram of the whole thing, we have a reaction force and a reaction couple from the fixed joint. And now that we've chosen the body to isolate, we've chosen that it's the whole thing, we know that the distributed load, if you treat it like a point force, is going to act 2/3 of the way from the point of the triangle to the wall side of the triangle. And the magnitude is going to be base times height over 2. So that's 15,000 over 2, so 7,500 newtons. Newton's second law says Rx, Ry plus 0, negative 7,500 is equal to 0. So that reaction force is just an upward force of 7,500 newtons. And then rotational Newton's second law, the moment equation about the z-axis. I'm going to put my about point at the left end. And so you just have mr and then a negative moment produced by that 7,500 with a moment arm of 1 meter. That's 2/3 of the way along the length times 7,500 is equal to 0. So mr is equal to 7,500 Newton meters. And now we can do the cuts. And one thing you have to be careful about with the cuts is if you look at this free body diagram of the whole thing where we've already used the equipolant load, that point force representation of the distributed load, it looks like we're going to have 2 cuts because we have this point force 1 meter from the left. But that's not really what we have. What we really have is if you looked at a free body diagram before we treated the distributed load as a point force, you would have loads at the left end, distributed load function that's the same the whole way along the length, and that would be it. So there are no points where the subfunctions are going to change. And so we can just use one cut for the whole beam. So, okay, cut 1 represents all x values between 0 and 1.5. Okay, so there's our cut. We have the upward force of 7,500. We have the couple of 7,500 Newton meters. And we have this distributed load that now doesn't get up all the way to a value of 10,000 newtons per meter. It gets up, you know, how high it gets up depends on what this x is. And so we can come up with what the height of this is for a given x. You know, this is our x location. We know that this is a linear function. We know that when x is 0, b is equal to 0. So that goes away. The slope we can get from the original distributed load. We have a rise of 10,000 over a run of 1.5. So I guess that's going to be what's that going to be? 10,000 divided by 1.5, 6,000, and then 6 repeating. So this function, which is our q, is 666, I'll round it, x plus 0. And then we have the internal loads, T, V, and M. There's no torques in this problem. And now I can redraw this free body diagram. We've chosen the piece that we're isolating. So we still have these point loads at the left. And the distributed load acts 2/3 of the way from the left to the right. The magnitude of that force is the base times height over 2. The base is x. The height is 6667x. So we have 3333x squared. And then the distributed loads, P, V, and M. So Newton's second law says 0, 7,500 plus 0, negative 3,333x squared plus T negative V is equal to 0. So T over the whole thing is 0. There's no internal tension. The shear force over the whole thing is negative 3,333x squared plus 7,500. And the moment equation, it's only the z moment that we care about. Our about point is at the left. We have positive 7,500 plus that 3,333x squared times its moment arm of 2/3 x. That's the distance from the left. That is a clockwise moment, so that's going to be negative 2/3 x times 3,333x squared plus m minus vx is equal to 0. And so we have m is equal to vx plus 2222x cubed minus 7,500. Now plug in what we know about v. So that's negative 3,333x cubed plus 7,500x plus 2222x cubed minus 7,500. And so finally we get that bending moment function is negative 1,111 x cubed plus 7,500 x minus 7,500. Now you can check the derivatives. They sometimes can pick up some math errors that you make. So dm dx is negative 3,333x squared. That matches the first term of v, plus 7,500. That matches the second term. So dm dx is equal to v. That's good. And now dv dx is negative 6,667x. Negative dv dx is positive 6,667x, and that matches q. So we feel good about these. Okay, so now what's the greatest absolute value of normal stress in the x direction for this beam? Well, so now we're going on to part B. The total stress tensor, well, let's say you can also do this piece by piece. So the total x normal stress is the x normal stress from tension. That one is 0 because the tension is 0, plus the x normal stress for the bending moment. So that's the only one we have to worry about. All right. Well, we know that the XX normal stress for bending is negative my over I. And our I value we can calculate. This is a circular cross section. So our I value is pi r to the fourth over what is that? Okay, I had to look that one up. I always get this confused with the polar moment of inertia, which we're going to talk about soon for a circle, but this is a 4. Okay, so the radius of our circle is 2 centimeters. So this is pi times 0.02 to the fourth power divided by 4. So that's 1.257 times 10 to the minus 7 meters to the fourth. And now we can plug in our functions. So, okay, we know that the stress as a function of x and y is going to be negative 1,111 x to the third plus 7,500 x minus 7,500 times y, and then divided by 1.257 times 10 to the minus 7. So now we have to figure out where this value is going to be maximum in absolute value. So we want to find the maximum value we want to find the maximum absolute value of that bending moment, m, and the maximum absolute value of y. The absolute value, the maximum absolute value of y is going to be when you're either at the top of that circular cross section or the bottom. So that's going to be, 0.02 or negative 0.02. They're the same. So that's what we're going to plug in for y. Now let's figure out what that function looks like. And you can do this in a plotting program, or if you wanted to go through the calculus and find the maxes and mins and stuff, you could do that too. All right, I'll be right back just a second. Okay, I'm back. When I translated this, I left off this this negative here. So that's everything I did up above was right, but when I brought it down here, I left off that negative. Anyways, the stuff in parentheses, if you plot out that bending moment function, looks like this. Let me do that again. So it comes to a value of 0 right at the end. And it starts at a value of negative 7,500. Okay, so that means that the maximum absolute value of bending moment occurs at the wall. When x is equal to 0. So this is 7,500. And now you can plug those into that function. And what you get is the greatest absolute value of normal stress. You can throw away the negative on the outside. Is 7,500 at the top or bottom of the cross section. So that's 0.02 divided by 1.257 times 10 to the minus 7. And you get a value of 1.19 times 10 to the 9th pascals. That's a really big stress. And so that for any material is going to damage the material. And that's the kind of thing that you can figure out from this kind of analysis. Okay, so that's a solution to number 5.